Okay, so this week in our lectures, we were charged with the task of finding the magnetic field at point P, right? So, start off with the things that we know. We already know that the electric field equation is E equals kq over r squared, and that E is proportional to both the charge and the inverse of the square of the distance from that charge, and that the field lines of E are parallel to the vector r. So, things we also know about the magnetic field, B, is that all of its lines are perpendicular to both V and R. But we also know that B is going to be proportional to, once again, the charge and the inverse of the square of the distance from that charge. Nothing too big, nothing too complicated there. Just things that we already know from our electric field stuff and our magnetic field stuff. If we're going to develop on that a little bit, we know that the magnitude of B, writing it in equation form, is going to be proportional with some proportionality constant with the two things we talked about. And then also, since it's a cross product, the easy way to write that is, your A, B sine theta, where theta is the angle between the two vectors. So, with those two, a whole bunch of scientists did sciencey stuff, and they figured out that the constant is equal to mu naught, which is 4 pi times 10 to the 7th. It's not actually 4 pi times 10 to the negative 7th, but it comes out to, I think it was 9 significant figures. Close enough. Which, for me, I think I'm fine with just remembering 4 pi times 10 to the negative 7th. But it was also that over 4 pi, so 9 times out of 10, it'll just be 1 times 10 to the negative 7th. Now, we're not taking into account a whole lot of directionality here, but we are taking into account the magnitude of B. So right now, we have an equation for just the magnitude, which is magnitude of B is equal to that proportionality constant times those terms that we just defined. Now, if we wanted to get into directionality, we're going to need a cross product. Cross product form of this equation is going to be exactly the same, where we said that A, B sine theta is equal to the magnitude of A cross B, right? So we simply took the magnitude of one vector and the magnitude of another vector and just popped a scalar onto the outside. We could put parentheses there, but it all comes out in the math just the same. Now I've highlighted those few bits, the Q, V, and R, to highlight the fact that there is a change from this upper equation. We're no longer getting rid of the directionality of Q or the positive slash negative bits of it. We're going to take that into account because it's going to determine which way our magnetic field faces. V has to be a vector now, so we have to take into account the x, y, and z components of V. And R is now no longer R arrow, it's going to be R hat. So it's not this, it's that. Now all that means is the magnitude of R with an arrow over it, the vector R, is equal to something. The Lord knows. But the magnitude of R hat is equal to 1. It is the unit vector that is parallel to the regular vector, our original vector. So we want to make sure that we are using R hat in the top so that we don't get rid of a term down here that we are going to need later. All right. So this is just explaining that bit up top. No longer R hat. No longer, it is now, it's no longer R arrow, it's R hat. and no longer q, no longer v, because we want the direction. And then a little bit of unit analysis. We know that our magnetic field is going to be in terms of Tesla. So if we swap in our units here, we have Tesla is equal to mu naught, which we're trying to find the units of. C for coulombs, meters per second for velocity, which is v, over meters squared because we have our r squared in the bottom. One of those meters is going to cancel out. And then we're left with coulombs per second on the top, which is going to be equivalent to amps. So we have Tesla equals mu naught amps over meters. We bring all those over to the other side. We have Tesla meters over amps, which is our final answer. So we get the units for mu naught, which mu naught in its totality is equal to 4 pi times 10 to the negative 7th Tesla meters over amps. So a little bit of a test of knowledge now. If we have this problem here, right, and we want to know the magnetic field at P caused by Q, we're going to want to identify our different components here. So number one is going to be R, which I've written them in the same colors just because I didn't feel like writing them all over the place. But our point P is at this point here. Our point R is going to be at this point, or is going to be that vector there. If we wanted our phi, that's our phi. We have our Q1, our Q is equal to 1 coulomb, and our velocity vector is equal to this. Line it up with the grid lines. Hopefully that's accurate. So we're going to write down the thing that we know. We do know this equation now. We know, because it's given, that our charge is equal to 1 coulomb. We know, because it's given, that R is equal to -3, -4. If we take the square root of the sum of squares of the components of our vector, and then divide the components by that sum of squares, we'll get R hat, which is I think it's normalized is the word for that, the normalized vector. And that is 3 over 5, -4 over 5, or -3 over 5, -4 over 5. The magnitude of that vector is 5, and that magnitude squared is 25. We're going to do our dot product now. We have I, j, k in the top, the components of our v, since that was the first term, and then the components of the r go on the bottom, which is -3 over 4, or -3 over 5, it should have been. Doesn't really make a difference. -4 over 5. If we take our I here, and we do this and that, it's 0 and 0. Our j, and we do this and that, 0 and 0 again. But for our k, we're going to have 6 times that and 3 over 5 times 0, which gives us this term here, which turns into this in vector form, which simplified is that. So if we plug in all of our knowns now, we know our v cross r, we know our magnitude of r squared, we know our q. We also know mu naught over 4 pi. We can plug that in to get that little bit right there, which gives us our final answer of 24 over 125 times 10 to the negative 7th in the negative z direction, Tesla. Very cool. And then for the next bit, we're learning about the Biot-Savart law, or rule, or theorem, or whatever it is. This is the bit where we get into integrals. It gets a little tricky here in just a second, but I promise you, if you bear with me, it's going to get a little simpler. So we're going to recall a couple of things from Physics 1, that our velocity is the change in length along a vector over the change in time, right? And things that we learned previous chapters, which are amperage, is our charge over the change in time. So the amount of charge that we've passed through over the change in time. So since we have Q and V up here, we can move that down here, switch in this term for our V, and then with Q over dt here, we can change that to I and dl. Very useful. So, if we know this now, a differential magnetic field, because since we're taking into account a differential length, our differential field is going to be mu naught over 4 pi I dl crossed with r hat over the magnitude of r hat squared. Now, this is the bit that's going to get a bit tricky, but bear with me. The goal of this, I'll write it down. Goal is to simplify to one term. I know we have dl right now, but dl, which is our little differential length here, bears on the magnitude of r. So say that we moved this way just a little bit. This distance is shorter than this distance. So we really do have 2 or 3 terms in here that are going to have some bearing, or that dl has some bearing on, and where the substitution math that goes into that gets really complicated. So we're going to do a little bit of trig. We're going to do a bit of identities here. So I'll go ahead and draw us out a little right triangle. That is the world's worst right triangle. And that's a little better. We're going to say that this is our phi. This is our r, our y, this is our x, right? So if our sine theta, right, is equal to SOH, so of the SOHCAHTOA, sine is opposite over hypotenuse, y over r. So we're going to put that in here. And then if we square that, we get sine squared, which is equal to y squared over r squared. That'll make sense in a second. Tangent theta is equal to TOA, opposite, over adjacent. So y over x. If we shift some stuff around, it'll be x is equal to y over tangent theta, which is the same as x equals y cotangent of phi. I'm sorry if I said theta before. It is phi, I promise you. So the derivative of that, dx, since we have a dx term or a dl term up here, is going to be y over sine squared phi. It's, I think if you look it up, it's going to be cosecant squared of phi, but cosecant is 1 over sine. So it comes out to be y over sine squared phi d phi, since we took the derivative of with respect to phi on the right side. So if we substitute in this sine squared into this sine squared and reduce, we're left with dx is equal to r squared over y d phi. There's no phi terms in here. I know it's confusing. I promise it simplifies out. So we plug that into our differential b. We have our constant terms, our I, which haven't changed, our dx or dl turned into r squared over y d phi. I wrote that down wrong. Hold on. There we go. Hold on. There we go. Hold on. Yep, that's good. Okay, so we have our r squared over y here, our d phi here, and then our r squared from the original equation, which is here. If you ever see me just write r squared, understand that it's the magnitude of r squared. So these two will cancel out. This is going to be constant for most of the questions that we're going to be dealing with soon here. So it's going to shift out here. And the I is also going to be constant for the equations that we're doing, so it's going to shift out here. So we get that our B should not have a vector. Our B is equal to this, which is all of those constant terms, times the integral of sine phi d phi. Or if you want to write it without the integral, it's going to be all of our constants times negative cosine phi evaluated from phi 0 to phi 1. Now, how do we know which one's phi 0 and phi 1? The direction that the current is traveling is the direction of your dl. I wrote that down here, but it's a little smaller. So we're going to start on whatever side your current is flowing from, and then go towards whatever side your current is going to. This is very important. R2 hat R2. This is the magnitude of R2. And then this, now this is another thing that's going to be a bit complicated. If this ray goes along this way, this is going to be your phi 2. Phi 1, I think I wrote it down as. We're just going to call it 2 though, because I put 2 on everything else. So since you're taking that, since the original phi is on the right side of your ray, or your position vector, it's going to be the same idea for the next position vector. Phi doesn't just automatically switch sides once we pass this vertical here. So, let's do it a little bit. Very easy problem. It looks complicated, but I promise you it's easy. So we start out with our p-value here, the point that we're testing the magnetic field at. We have a point A and a point B with a current I flowing through it. We know just that. That's all we're given. So our Y, which is the distance from here, or from our line to that point, is 30, which is given in centimeters. So 0.3 meters. We know that our I is given. It's 1 amp. And then we can use a little bit of trig, arc tangents, to find phi 1 and phi 2. So keep in mind that tangents are a bit messy, and you have to kind of figure those out yourself as far as pi is concerned. It gives you some wonky angles. But if you plug that in using essential theorems of calculus or fundamental theorems of calculus, you end up with 5.648 times 10 to the negative 7 Tesla. Okay, so we're just going to do a couple of practice problems here concerning the handout that we got today. A segment of wire carries a constant current I equals 1 amp along the x-axis between x0 and x1. Compute the magnetic field B at point P with coordinates xy, 0, 1 centimeter. We're going to say this is 0, 1. We're going to call that 0.1 meters, actually. 0.1 meter is point P, where x0 is negative 0.05. I almost messed this up. 0.01 centimeters, 0.01 meters. This is negative 0.05 meters. And then this is 0.03 meters. Right? So our initial position vector is going to go from here to here. Since our current is flowing this way, our initial phi is going to be the angle between the tips of these two vectors, which if you drew them tail to tail would be like this and this. So our angle, I'm sorry, yeah, hold on. If you drew them tip to tail, right, it would be here and here. So your angle phi would be here. And I guess it would work the same if you drew it the other way as well. Yeah, it works out either way. So that's equivalent to this angle here. And then, since we have to stay on the same side, this is our R2, which our angle phi 2 will be there. All right? So if we want to know B, we know that it's equal to mu 0 I over 4 pi y integral of sine phi d phi from phi 1 to phi 2. That's something we know. We already covered it. So we know that B is going to be equal to mu naught over 4 pi, which is equal to 1 times 10 to the negative 7. That whole term, because mu naught is equal to 4 pi times 10 to the negative 7. I over y is 1 over 0.01. So it's going to be 100. And then we're going to have negative cosine of phi from tangent negative 1 of 0.01 over negative 0.05. My bad. Hold on. My bad. Hold on. My bad. Hold on. 0.05 to tangent negative 1 of 0.01 over 0.03. I'll do those calculations and I'll be right back. Okay, so I have done a little bit of calculating. So we are going to get this reducing. We're going to have B is equal to 1 times 10 to the negative 5th, because this is equal to 10 to the 2nd, and that cancels out with this. And then we're going to get negative cosine of phi evaluated from 0.197395, we'll put that 6, to 2.819842. And then if we plug that in, we're going to get B is equal to 1.9293. 9293 3 times 10 to the negative fifth Tesla. Right? But it's probably going to want the direction of B. So using the right hand rule, if you point your thumb in the direction of the flow of current, you can assume that the current is rotating in the same way that your fingers are rotating. So if you imagine a disc rotating about I in the same way your fingers are curling, it would come through P in the, if that's X, that's Y, that'll be Z. So it's going to come through in the positive Z axis. So we can expand our answer just a touch and say that it is in the direction of 0, 0, 1.